love teaching, and I love trying to think about faith and science and bringing these things together. So thank you for coming out here tonight. And we are going to talk about abiogenesis, and actually 3 major areas that I have been looking into, and that a lot of people have for many decades, and perhaps for centuries. People have been looking and thinking about some of these things. And so just wanted to give you, I think there's 3 major areas in science that I think present a challenge to what are called naturalism and materialism, which is really the study that can we explain everything just by looking at the materials, or is there something more? And so that's what I want to talk about, these 3 major areas that have impacted me as I've researched them and looked into them, read a number of books and talked to people. And in fact, I'm on a little team of scientists where we're trying to address some of the issues, especially in the origins of life. So I'll say a few things about that. And for the first one, is on fine-tuning. So I have a lot of things I like to say on this topic, and in fact, for my students, to get them to come hear them, I also offer extra credit. So this is a good tradition that your teachers have started, and many teachers have done. So I have 10 talks that I do that are 1 hour long, 50 minutes, and then they get extra credit for coming to them. So that's 10 1-hour talks, so I can't do that tonight. So I'm just going to give you just a little preview of how some scientists look at this fine-tuning argument, that when we look at the world and the universe around us, it looks as if it's been fine-tuned by a designer to work well for life. And this is, so I have a few videos that, I'll probably have 2, I think, that I'll show. This one's really good. I thought I would just show that, and then I'm going to have a few other discussions after that on the fine-tuning argument. I hope you find this interesting. And so, yeah, I know I came to talk, but I'm going to let this one do the talking for 6 minutes here. It's just really well done, and I'll have a few comments about that. Simple faith. And I find that quite amazing. Let me make sure that's working. Yeah. So if you wanted to look up and find that video, fine-tuning reasonable faith. Oh, that's not. Yeah, look up the fine-tuning of the universe. All right. So that, to me, is more physics, though, and doesn't always speak as strongly to a chemist, because we're into molecules and atoms, although this talks about the formation of those. So, but a lot of scientists find that very compelling information. Some of the things that speak a little bit more loudly to me that we're in a really amazing place is when we start talking about Earth. And when we look at Earth and where we find it in the solar system, snuggled in between Mars and Venus, this is called a really nice place here, the Goldilocks zone. From the story, hopefully you guys remember about Goldilocks and the porridge being too warm and too cold, and this is the right place in terms of being warm enough. But it's not just warm enough because we're the right distance away from the sun. You see, if we didn't have the atmosphere that we had, it would actually be on average around minus 20 degrees Celsius. You guys think in Celsius or Fahrenheit, or both?
Fahrenheit.
Fahrenheit? Like, can you think in Celsius? Because I'm a Fahrenheit guy too. I grew up with that, but in science we like to use, so that minus 20, that's cold. Okay, I don't know if you guys have experienced anything like that here, but we get close to that in Michigan. So that is, so 0 degrees, right? Freezing point of water. So everything would be frozen here, or likely to be frozen, if it wasn't for our atmosphere. So we have global warming here, and that's good from a general science sense that without global warming, we would be very cold here. Now, do we have too much global warming? That's a debate that I'm not going to get into right now, and that we saw some trends there. And but we need to be thankful. I want us to step back and go, wow, we have a really amazing atmosphere, and there's something awesome to that. And I'll say a few more things about that. So it looks like our place in the solar system appears to be finely tuned with the air. And then I've been looking at some other research that seems to indicate that maybe even our location in the Milky Way galaxy could be a special place to live. It turns out if you're a little bit closer to the middle, there's a lot more radiation there, and that can be very dangerous to life. We already know that there's enough radiation around us that could be toxic to life. And then from a materials perspective, if you're too far away, scientists have analyzed that there's not a lot of minerals and heavy metals and things that you need for planet and living systems if you're too far out. So it appears that there's a Goldilocks zone, perhaps even in the Milky Way. Too toxic in the middle, and not enough elements too far out. And there appears that even as this is not a picture, this is a drawing of the Milky Way. If you were to look at it, it'd be flat like a plate. And even if you go too high or too low, as our solar system goes and spins around the Milky Way, it could be too much radiation if you get too high or too low. So there's even this fine-tuning of how we go through as a solar system through the Milky Way, which I found absolutely amazing. Additionally, some more recent research is suggesting that maybe even our galaxy is in a special place within a supercluster of galaxies called Laniakea, in a Hawaiian word. I think that means heavens. And so this argument is not necessarily a very strong one, but just kind of interesting to think that there's structure maybe even to the universe. So looking at all the different places that we find ourselves in the universe, superclusters in the galaxy and the solar system, there appears to be fine-tuning there. I'm not going to go into a lot of detail here, but I just want to tell you that even the light from our sun is so fine-tuned for life. There is 7 parts to the electromagnetic spectrum: radio waves, microwaves, infrared, visible, ultraviolet, X-rays, and gamma rays. The energy that comes from a sun that is in the radio and microwave and infrared radiation just doesn't have the energy to do a lot of chemical reactions. And then on the other side, UV, X-rays, and gamma rays are just absolutely dangerous to chemicals, and they can break bonds and cause a lot of ionization, and they break bonds. That's bad, because if you break your bonds, you're dead. And so that radiation is, if a little bit does come from our sun, but it's blocked by our atmosphere. I'll show a little picture on that. And if you guys remember your kilojoules per mole for bond energy, I don't know if you do or not, but if you did from general chemistry, a lot of bond energies and doing useful chemistry happens in the visible range. That's why our eyes work. And photosynthesis is activated by blue and red, because those are where the energies of the electromagnetic energy function to move electrons around without blasting them off. And so you can do really valuable and interesting chemistry with visible light. So that is an amazing coincidence there. Our atmosphere is amazing, and it blocks the gamma, UV, and X-rays. And there's a little window that allows visible light through, and then there's another big window that allows radio waves through. But a lot of the other wavelengths are blocked. And so we get the harmful radiation is blocked, lets light in, visible light, so we can have life and see around and trigger a bunch of good chemistry like photosynthesis. And then we're trapping the heat with the infrared blocking that happens there. And these are all long talks, so I'm just giving you guys the quick version of them. And we also live on a planet that has an amazing set of features to trap water. I'm going to quickly go through this. I usually spend like a half an hour to go through all of the components, but you guys are smart college students. And so this is what's amazed a lot of people, just how amazing our Earth is. So as water turns into steam, it floats up into the sky because it's less dense than our air, so it floats up. But it gets cold in the upper atmosphere. And we kind of know that. So yeah, it gets cold up there. But did you know it actually gets cold and then it gets warm again, and then it gets cold again, and then it gets warm? So it doesn't, if you go up high enough, it's not just cold. It could be warm. And it's that cold that freezes water out, so that's important. But the oxygen goes through. And as oxygen goes through, it gets bombarded with UV, and it makes ozone right above where the water freezes out. And that is in the right place, that UV light, and where the ozone gets made, it actually blocks more UV light, further protecting the water, because if too much UV light hits water, it splits it into hydrogen and oxygen. And that would send part of our water out into space. So the ozone layer's in the right layer, which is right above where water freezes out, and that's super important. And all of this is protected by a magnetic field. We have a great magnetic field that blocks the solar wind, because that could just blast all of our water and a lot of our air off. And we don't have an electric field that Venus does, and I won't go into all that, but Venus has a really strong electric field that can break molecules and send them off into space. So scientists are really looking at Earth and going, wow, there are so many amazing properties that this is looking very finely tuned. And I would say, as you start looking at the different factors that when it comes to looking at how much air and ozone and oxygen and how they interact with each other, I start to see gears, because if you had too much, some things would be not so good, or too little, not so good. So I see a lot of fine tuning that takes place with that, and how they interconnect with visible light, Earth's electric and magnetic fields. And so as a chemist, I start to see all these things, and they look like gears. And if someone looked at something that was made out of gears, you would go, I don't think that happened by chance. It looks like somebody made that. Because that looks like a machine. But it's just that we don't understand the chemistry of our world, that we start to think, well, maybe if there's enough galaxies and enough suns, that maybe there could be an Earth, another Earth-like system. And we block from a bunch of dangerous things. So this argument is, I think, a really interesting one. But I think a lot of people would say, but there's a lot of galaxies out there in the multiverse, and we heard some arguments against that. But this probably isn't, the biggest and strongest one. I think it speaks loudly to me, but there's some other things that I want to share with you as well. So I think this thing's a little flaky here. If I set it in here and I don't bump it with my hand, I think that would be better. All right, so I'm going to move into the next part about abiogenesis, but it starts with this study that I actually talked to this guy, John Narcombe. He's a marketing professor at Arkansas Tech University, and he was wondering how people thought about science and what could science do and not do. Very interesting, close to our questions that were asked here. And a question was asked, and 715 people responded. This was the question. Scientists researching the origin of life could they have created complex life? Do you believe this? Complex life forms from scratch. This is what they were asking people. That is, in the laboratory experiments that approximate Earth's early atmosphere, scientists have mixed chemicals to believe to exist before the first life forms, and they have successfully created complex life forms like frogs. And about 40% of people have identified and said, yeah, that probably makes sense. I'm not aware of how they would have known that, but so that's the perception that's out there. Now, this gentleman asked another question and said, all right, so 40% of people, that seems quite large. What about, have scientists made simple life in the lab? They're not complex, like a bacteria. Could they have done that using chemicals from scratch, like things that could have shown up in the early Earth? And we got almost 73% of people say, yeah, this has happened. And it has not, by the way, it has not happened. So there's a perception problem that's going on. I want to highlight that a little bit here this evening as well. So we talked about what is abiogenesis, and so I want to say a few things about that. It's an area that I've been getting pretty deep into here. So Genesis, right? Genesis from the Bible, but Genesis is the formation to make something. So biogenesis, making life. Abiogenesis, making life from non-life. This is where this whole discussion is about. Some people call it chemical evolution. We've heard about evolution, and so if that's true, what happened before that? Chemical evolution is the discussion. And the experiment that kind of really triggered scientists into thinking, wow, maybe this could happen, was through the Miller-Urey experiment, where some scientists from the University of Chicago, which is not too far from where we live, up north in the United States there, and from Michigan, they took some gases they thought could be on the early Earth, like methane, ammonia, some hydrogen and water, no oxygen, and they put some sparks through that with some water, and they made some amino acids. How many people have heard of the Miller-Urey experiment? Is this something you saw in your textbooks or something? Okay, got some hands over here. Okay, you were supposed to, I don't know, maybe you weren't supposed to learn, but it's in a lot of textbooks in biology and biochemistry. Where's our biochemist? Did he leave already? He might have left. All right, I'll ask him if it's in his biochemistry textbook. So it's a really popular experiment because this surprised a lot of scientists. They're like, whoa, we can make amino acids without a living system. This just shocked the world. And so a lot of people were excited about, wow, maybe if this could happen, then these amino acids just need to get together, and then life can happen after that, because we're starting to get the ingredients of life. And as good scientists, they repeated these experiments, and people have over many years, for decades, and they did get amino acids, so very reproducible experiment there. And so they made amino acids. So this looks like this was interesting, but upon further and thinking about these experiments, people are excited. They actually made what's called left and right-handed amino acids. They're called chiral enantiomers. We just call them right and left-handed. And our life actually only uses one of them, the left-handed ones. Is there any left-handed people out there? Because, yeah, all right. Well, I'm not left-handed. I like to be ambidextrous. I pick choose both hands. And so we call the amino acids that are important for life are left-handed. I don't think it has anything to do with being left-handed or right-handed, but it has to do with how they polarize light. Maybe you've learned that or not. But anyway, so somehow life is selected all of the left-handed ones, but these experiments made left and right-handed, so that can cause a confusion, a really messy confusion inside of that pot. And interestingly enough, they didn't find any proteins, because you need proteins, you need the amino acids need to come together to make proteins. They didn't even find a dipeptide. That means they didn't even find two of them hooked together. So it's interesting that they made amino acids, but there wasn't much of a start as people, I think, thought about that. It turns out if you have proteins, they break down after a while in water. So this is a big conundrum. Water breaks down proteins into amino acids and then breaks them down after that. And then lastly, what is not talked about in the experiment is that this was a really messy experiment. Less than 0.1% actually were amino acids. There's a bunch of other junk in there. And that can actually be toxic and trap the interesting, what we call biotic materials, the amino acids. And if there was any oxygen in there, this experiment didn't work. And as geologists have looked at where might oxygen come from and when did it occur in Earth's history, it appears that oxygen, from what I could tell, has been there for much of Earth's history. And so this makes a highly unlikely scenario for the gases they picked. And it only made amino acids, it didn't make nucleobases that are needed for DNA and RNA. And more recent here in the last year, scientists have found out that this experiment didn't even work unless it was running glass. They ran it in a Teflon container and didn't even work. And so the gas catalyzed it. The glass catalyzed the reaction. So wait a second, so if you did have lightning strikes in the right gases around, you still need to have sand, and it was borosilicate sand, was there boron, so this is a pretty big challenge that people are excited about this experiment, but maybe we shouldn't be too excited, because it didn't really go anywhere from that. And you need the amino acids need to come together to form proteins. This is the only chance a chance has. Now, how many proteins and other simple chemicals are in one of the simplest cells, like a bacteria? Have you guys ever thought about that? I asked this question when I was thinking about some of this. Like, well, how many, like in a simple organism, how many ingredients, how many chemicals, proteins, and enzymes, and we got water and minerals. Does anybody have an idea? I'll take some numbers. Shout out some numbers. How many different chemicals are in a simple cell?
10,000.
That's a pretty good guess. We should have had you wait here. Nice. That's pretty cool. A little bit fewer than that. So we're just going to jump into it because we got a few things to talk about. So it's maybe around 3,000 to 4,000, depending on how you count them. So 3,000 to 4,000 different amino acids. This is in a simple bacteria. I think this was, so I found this from a biology textbook. the chemical components of a cell. This was a hard thing, because I never, like, how big is this problem to make life? This is what scientists we're starting to get a grip on what is life. And we recognize there's a lot of systems that are in place, and we need a lot of chemicals there. And so it's just not proteins, it's not just DNA, it's all of these things that need to be happening at the same time. So I'm going to take a short break right now and let my wife say something if she's ready. And we call this the Microbe Minute, because she's a microbiologist. And then we'll tie it in to the talk here. All right, dear.
Well, hello. As he said, I am a biologist. I got my degree in biology, but my work experience is actually microbiology. I worked for 3 years doing research and development, trying to find antimicrobials, long-lasting antimicrobials. We tested them against bacteria. And then that was in Texas, and then I moved to Michigan and worked for 3 years doing some quality assurance, quality control roles, testing with known bacteria. And so we thought it would be fun to throw in a little microbe minute just to highlight a bacteria or a microbe that is beneficial to us in some way, or that is interesting or unique. And so when we came here, I thought maybe I should let you know we did bring some bacteria with us. We hope that you're okay with that. I see some faces, yeah. But thankfully, the bacteria we brought with us are like cute ones, like this. So the bacteria that we want to talk about today is like this one. This one is E. coli. These are actually 1 million times bigger than the actual size of the bacteria itself. And one of the reasons we want to talk about E. coli is it's kind of well known, people have heard it. It does get kind of a bad rap because if you do ingest the wrong strain, it will make you sick. But some strains of E. coli are actually very beneficial. Does anyone know, so we do have E. coli in our bodies, does anybody know where that is found? Even lower. So it is the intestines, but it's actually the large intestine specifically. Okay, well, one of the interesting things is that some bacteria can make vitamin B12, and E. coli is one of those bacteria. And this has a whole list of some of them that do it by certain pathways. Now, vitamin B12 is really important to our systems. It helps with red blood cell growth, nerve cells, helps make our DNA, and so it's very important to have this vitamin. Now, vitamin B12 is found in animal products only, okay? And so if we consume animal products, you get enough vitamin B12, typically. Any excess vitamin B12 is actually found in organs like the liver and stuff, so those do have a high vitamin B12 count. Now, one of the problems, though, is if you do choose to eat more of a vegan lifestyle, you may become vitamin B12 deficient, and this can lead to problems. Like we said, it's very beneficial to our system, so we need vitamin B12. But thankfully, scientists have been able to make this using some methods, and they can fortify foods like breads and grains and cereals and stuff like that with vitamin B12. And so, yeah, I guess I already talked about that. So it's just important to make sure we do get vitamin B12. But this is one just to highlight that bacteria were once thought to be very simple, but they are actually very complex machines. As we've seen here, they can make some pretty interesting things. So, turn back to you.
Thank you, dear. And this has surprised a lot of people, and this is a really weird conundrum that people have. The vitamin B12 is actually being made in your system, but it's not in the right spot, and that could be something that evolution has caused. I think this is some of the degradation that life and time has caused in us. So I think we need to start looking at living systems like bacteria in our cells as chemical factories. Because many of the ingredients and molecules that are found in nature, there's rocks and we have minerals, but you can't find vitamins and proteins lying around. There are just thousands of them that bacteria need, as we just discussed, and they are made by the bacteria themselves. They get some of the raw ingredients, and then with the machines that are inside them, they make vitamin B12, other vitamins, and then the DNA and RNA and the things that they need all get made inside of them. And this was a big shock well, not shock, it's just what we've been learning in science. And so as Darwin wrote his Origin of the Species in 1859 and 60, this is, at that time, kind of what they thought of what cells were. They were like soap bubbles. But if you read any biology textbook now, we recognize that as we've learned more about how to view things at a small level, that the cell is actually a factory. And I would like to argue that it's a chemical factory. That they're making, the cells need to make things because they are not found naturally or in nature. So there is a book that a gentleman I'm getting to know, Rob Stadler, wrote a book about what are the different things that need to come together for abiogenesis to be true, from going from chemistry to biology. And he wrote out a number of the steps, and as I'm showing here, that this is where, in that survey, 73% of people thought we were up at the top, where you could take simple chemicals and turn them into biological entities, life. But most of the research is way down here. And so so Rob and I and a few other colleagues, this Rob Stadler and I, and a few other of our colleagues have joined up with a cartoonist, and we've been reading a lot of the recent literature in this area. And I'll highlight it a little later. I want to show you a video that we put together, and to highlight where the research is showing, and it's kind of fun. It's a funny video, but we think there's some important truths that we're learning along the way about what chemistry is teaching us about can the molecules of life come together. And so I want to show that. It's 10 minutes long. It's pretty funny. I think you guys will enjoy it. There'll be some good things to learn along the way. And it encapsulates a lot of this thoughts here. Now, I should say real quick, we haven't made one video. We've made 4, and we've got 4 more coming in the works, because there's a lot of different parts that researchers are looking at, and we want to just address some of those as we're going along here. So I'm just going to roll some film here. The YouTube video that we're launching them is called Long Story Short, but if you type in Long Story Short to like YouTube, you'll get some movie about a long story that's short or something. So if you put abiogenesis, you'll find it, or chemical evolution. And so we'll have a little video break here to watch this.
I've got some.
So just real quick, long story short, and we're trying to review these the papers that are coming out, and they're not sounding too hopeful. You guys have been here a long time, so I want to kind of jump to the some of the conclusions here. Just to highlight a few things here real quick. When I read some of the news articles that come out about origin life research, they often say we've solved the problem. But there's a lot of conundrums that we've heard, like things that happen that we're not sure how they can happen. And so researchers solve the puzzle of life, and then they keep solving these problems. And then if the problems are solved, why do we keep solving them? And so there's a lot of these interesting things that happened just even this month, where a scientist at Purdue, in a really interesting set of research, showed that he could put amino acids together in water. And that would have solved this conundrum that we saw in the Miller-Urey experiment. But then when I read the paper, he did it in a gas chromatography instrument, which was under a vacuum, and he only made 3 to 6 amino acids put together. And proteins and things that are needed for life, they need hundreds of amino acids and more. And so in the paper, or in the press release that went along with the paper, he says this is essentially the chemistry behind the origin of life. This is the first demonstration that primordial molecules, simple amino acids, can spontaneously form peptides, the building blocks of life, in pure water. This is a dramatic discovery. I think one of the issues that I have is, I think this is great research that needs to be done, but I think it's the hype that I think that is not scientific, that we need to be careful And I know there's a need to publish and write more papers, but I think what we're trying to do is, just tell us what you did in your research. You don't need to over-expand it and say that you've solved all the problems. I think that the public is intelligent enough to just, let's learn what you've done, and how does that get us closer to understanding what's there and what's not there. And so none of these things that they did simulated Earth's conditions, because it was under a vacuum in this instrument, and they detected them a few milliseconds after they were made. Nothing about how stable they were. And so I wanted to do one little demo. Dear, can you do this one for me? So I think is there a research that we would find convincing that maybe life could get started from the materials out there? And so my wife here is I thought this was a fun thing our kids like here. And when amino acids come together to form proteins, we should see all of this coming together and making really long proteins, but that is not what we see in the research. It's a little bit like, if we could see this, go ahead and throw that out there. Isn't that crazy? No, it worked great. It all came out. Now you get to put it all back together. And so it's things like that we haven't seen, where everything's like snapping together and going inside cell-like membranes. We don't see that. We see falling apart and low yields. And there's another scientist, James Stewart, who's published a lot more papers than I have, and he's been very targeted at saying, hey, you guys you're saying too much about your research, that we don't know really about anything. And he is from Rice University. He's a Christian, and he's not saying how things got created, but he's just saying, look, we don't really know. We don't know. And this is a big change in the research in the United States, where they're now starting to put a lot more money to it because it's not working out very well, or there's a lot of work to do, because life is very complicated. So the number of articles are just greatly increasing in this area. They're not huge numbers, but it's greatly increasing because there's a lot of challenges there. So one of the things that we learned then from chemistry, that it's really messy to make these natural reactions. They're usually in really low yields, and they're prone to mistakes and making things in incorrect ways, but we don't hear about that. We just hear, oh, they might have made some things. Biomolecules degrade very fast. Your life is constantly making them because they fall apart. There's a system to scan them and go, oh, that one's broken. Get rid of it. Let's build some new ones. So what we see in living systems is, let's make their good, clean yields, or high yields, it's clean, and anything that's mistaken is cleaned up. Life is a coordinated set of delicate reactions finely tuned to overcome all these natural forces that want to break it apart. So I think this is giving some evidence that there is a designer. Because people, and we put together things, and I believe this is what God has done, is He's put the molecules together to overcome a lot of the natural forces that are there breaking it apart. So we see bakers and scientists making things that the molecules don't want to do by themselves. So I think that's one of the biggest challenges that's there. And I'm just going to go real quick over the last one. And that has to do with information. So let's say you could make all of these molecules and turn them in. You want to get that? But does that make a living system? Or could you make life even if you had all your proteins and polymers? Now I have a little magnetic board up here. Do you guys know what word is on here? I've scrambled it, by the way. Do you guys know what word this is in the letters right here? Can you unscramble it?
Gecko.
Ah, very nice. It is gecko. Let's hear. Well, I have a much better demonstration, but it didn't fit in the plane. Gecko. I gotta see if I can remember how to spell it. Right? So we need a biologist. Did I do it right? Okay, gecko. Now, how did you know that? Because you know the code. Right? And did the magnetic board tell you what the code was? Like, did the magnets tend to? No, I could do that, right? And it's not the letters that put. That told me what to go. It's like I had this code in my head that we call the English language, and our brains were able to decipher what order it should go in. And that's what's, I found a connection in actually reading a book by Stephen Meyer on DNA, the information that's in DNA, and it opened my eyes. Our DNA has the phosphate ribose backbone, and then it has these rungs, if you would, of the ladder of the base pairs. And if you were to take a look at the ladder part of it, the outside, and you cover up the rest of it, there's no way you can tell chemically what the code is, what letters are there. The DNA system is set up so that you can have any code, just like I could have any letter of magnets on here. And it's allowed, and any sequence is allowed. So why do we have the sequence that we do inside of us, inside of you? Where did that sequence come from? Where did that information for that code come from? And so even if life had natural ways of making DNA, the chemistry that we see is very random. It's allowed to be in any order. Chemistry does not dictate you have to have an A and then a T, an adenine and a thymine and guanine. There's no order. There's no chemical patterns that are forced or allowed by anything's allowed, just like anything's allowed here. When we see that, we see, oh, that looks like that could be information. There's a code there. So chemistry doesn't dictate any of that. So that was a revelation to me that inside our bodies and inside any living system where there's DNA, that's a code there. And this is being hotly debated on whether there's a code there or not. But if it looks like a code and smells like a code, it probably might be a code. And there's a lot of information there. We know there's DVDs full of code, gigabytes of information in that code. And so they can go in any order. And so who or what determined that order? And I think that's the real challenge that as scientists look at that. Where did that code come from? Because it's not just a few base pairs that need to come together to form a living system. It's thousands, in fact, hundreds of thousands of base pairs. But we know people make codes. We know brains and intelligence makes codes. And so I think what we're seeing now is that some of these things that we're now learning about cells and how our bodies work and living systems work and how chemicals work, that nature and natural forces are really, there's not a good explanation for that. And maybe there will be in time, but it's not looking good. I skipped some stuff on thermodynamics and things just so we could get more towards the end here. And we have more videos that are highlighting these challenges, the conundrums, like, you're making this, but you're also making something that destroys that. And that's what's not often talked about. So I think the way that we get out of this hole here, this information hole, is there's a designer. And as a Christian, I point, to me, that it points to God. And for others who think that there's intelligent design, it doesn't have to point to God. But so the problem with holes, and I see a number of holes in the origin of life, is that if you don't get out, you're dead. But we're not dead. We're here. And I believe that is by God's providence. So I am a Christian, and I do believe that God started life. And how he did that is still a mystery, and we're learning about it. But I do believe that we're fearfully and wonderfully made, and it's just amazing to be able to study that and to look at it and to see it from a chemistry perspective. And there's a lot more there. And there is debates on this that are going on. But I think that as we were hearing, that I think there's some coming together of scientists that let's have these dialogues and let's see that both sides have scientific information that we're using to make our decisions. It's not like you're a Christian and I don't believe in science. I think, no, the Christian world embraces science, and for the most part. And so I embrace it. I love being a scientist. I love how it helps me to see the world. And so I think we're taking issue with some of the overhyping that's going on. And so we want to call that out. And let's get back and see what we're actually learning from the molecules as they react. So I'm going to leave it right there for now, and maybe we can have a few questions. And you guys have hung in there for an extra long lecture. So thank you so much. I really appreciate the invitation to be here. And I hope you learned a few things. And I just really thankful to be able to share some of this. And this isn't just me. There's a lot of other scientists who are doing this work. And this is under the field of what we would call intelligent design. What are things that can happen by design, and what are some things that happen by chance? So that both of them happen. And I want to know where that line is. And I feel like I see that when it comes to the things that we see in living systems, is that there's just so many things pointing to design. So God bless you. God bless you in your studies and the decisions that you're making. I know you guys are all looking for careers. And some of this stuff is because I ask my students, like, where on the scale are you interested in this? And it's often, there may be 5 out of 10, or we got some students that are 9 and 10 out of 10s. But, and I guess this is probably an anticlimactic last statement. I didn't need any of this when I was working in industry. I didn't need to know any of this. You can be an awesome scientist and make amazing changes to this world, and we don't need to know any of this. We're still learning how medicines work, right? And our bodies work. And so I didn't face any faith issues, especially as a chemist. We can do so much without having to know this thing. But I think deep down inside, we want to know where we came from. And so it's in that area that I think where this discussion takes place.